Now for the second technique that I'll be demonstrating, it's going to be called stack spoofing. So to demonstrate what stack spoofing is, we sort of need to understand what a call stack is first. So I'm going to run a normal beacon right now, and we should see something Cobalt Strike. So if I go ahead and check this beacon out in Process Hacker and open up the threads, you can see there's a bunch of threads, and if you double click any of them, this is a call stack. You could think of it as a listing of function calls that brought the program to, or the thread to its current state. So up over here, let's look at Beacon's main thread. So anything within NSTIC kernel, that's a kernel mode call stack, and it's visible because we're in administrator. But typically, we would only be able to see up to say this one, which is ZW delay execution, because right after that, it goes up into the kernel. So it goes from the top all the way down. So we could see to get to this call, delay execution, it came from a sleep X call within kernel base, which came from these numbers. So these are actually, they're either going to be memory addresses or just arbitrary values within the stack. And the reason that this happens is because oftentimes malware, when it lives in memory, it lives in allocated memory, which isn't pertinent to a file on the file system, like how SleepX, its memory region is within the kernel-based DLL. This has been this is starting to become more and more of an indicator of compromise because unbacked memory regions aren't too common. There are certain legitimate use cases for them, but uh, that's not it depends on the process. So in this case, seeing that in this case over here, we could see HTTP send request A was called by an unbacked memory address. This memory address meaning that it's not backed by a file on disk. So call stack spoofing intends to sort of address this issue by basically spoofing that call stack. So this isn't something that you necessarily need to be worried about from your loader because your loader is gonna probably gonna be either an EXE or more likely a DLL, and that DLL is already gonna be backed on disk. Regardless, you may want to integrate this technique into, say, a UDRL or directly into your implant, so you don't have those same issues that we were just seeing with Cobalt Strike. So we've created a small proof of concept within this course that shows how this sort of the effectivity of it. So by running this binary that we'll be explaining the course called synth.exe, it'll first create a message box. And this message box is, it's a normal message box. And if we take a look at the call stack of it, we can see a bunch of entries. RTL user thread start, some things coming from synth.exe. And this is usually why your loader wouldn't need to have wouldn't need to integrate call stack spoofing. It's because your loader is already a file on the file system. So it's all of its calls will have a valid looking entry in the call stack. And then we could see there's the message box A call all the way up to this last NT user wait message. I'm going to take a snippet of this right now because we're going to use it as a comparison. So if I click OK, now this message box, it's still a message box, but within the code, we've spoofed the call to have a fake call stack. And if we take a look at it and compare it with what we just took a screenshot of, you can see all the calls that it's making up top. So here we have the message box over here, message box A, then message box timeout. All of these are the call leave frames that resulted from us calling message box. And if we look below it, we'll change the color over here. If we look at these first three frames, to the untrained eye, they're pretty interchangeable because they're pretty interchangeable because you have these two frames at the bottom, and then you have this thing coming from kernel base, and then you have these which are the loader. If someone's just looking at this visually, they might not see any particular issue. which is why this can be useful, because if we think back to Cobalt Strike's call stack, if we implemented this within Cobalt Strike via UDRL, rather than seeing those random floating numbers in the call stack, we would see something like this, which looks much more legitimate. And then the rest of this loader is going to be performing a sort of local shellcode injection to spawn a calculator, and then it's going to call get character with a spoof call stack again. So, but if you just look at it, it looks pretty normal unless you do a lot of forensics on it. The way this technique actually works is that programmatically uh, we parse exception information that a lot of programs use for exception handling, and we leverage that information to build up a fake call stack and to hide our original one.